www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay, so let's get started today. Today we'll be talking about bulk recombination, and this means that if you have a bulk of semiconductor on which, let's say, you have perturbed equilibrium by some means, let's say by shining light, then how the equilibrium is restored. Now, bulk could be bulk of many things, gallium arsenide, silicon, and all other, that type of things. But as you know, silicon is sort of the dominant material, indirect band gap material. That derivation is a little complicated, and that's why I want you to guide you through that. Gallium arsenide and other direct band gap material, very easy. So I'll keep it for the end when you are a little tired, maybe towards the end. So we'll begin by derivation of Shockley-Reed-Hall formula. Now, three names are associated, Shockley and Reed. These are the two people, very famous. They wrote a paper, I guess, in 1954, deriving the formula. And Hall, in fact, 1 year earlier, I think, he derived the formula independently. And so there is often called SRH formula, short for Shockley-Reed-Hall formula. And I'll show you how to use Shockley-Reed-Hall formula for various special cases. Now remember, Shockley-Reed-Hall formula only applies to indirect band gap material, trap-assisted recombination, this type of thing for silicon and many other indirect band gap material. It's not a general formula that applies everywhere. Right? Okay. And then we'll talk about OJ recombination and direct recombination. Remember, we said in direct band gap material, this is very important. OJ is when two electrons bump against each other. One electron goes down, the other electrons goes up, very high in energy. So we'll talk about that, and then we conclude. Now, let's think about it slowly. We are talking about an electron, red electron. The dotted line is a trap. Generally, I used to draw it short. Here I have drawn it long because I'll have to draw a few more things. But remember, that's a localized state at one point, right? It's a defect or a trap. Now, what we see here, the electron is coming down to the trap, being captured by the trap, waiting there till a hole shows up, and then dropping into the hole. At the end of the process, an electron is lost from the conduction band, a hole is lost from the valence band, and nothing has stayed in the trap. The trap has returned to its original position. So this is going down. We'll call that process 1 and 3, just to give it a name, because we'll be using this later on. We'll just call this process 1 and 3. Now, there is always an inverse process that where an electron from the valence band now jumps up to the trap, and from that electron eventually goes up to the conduction band. So at the end of the day, the net result is one extra hole generated in the valence band and one extra electron generated in the conduction band, and nothing left behind in the trap. So trap temporarily held it, the electron, but at the end of the day, it is not really holding anything. And we'll call that process 2 and 4. And many times when I'm working out this math, it will be helpful if you consider the dotted line in analogy of the USA. Remember, I had these boxes for USA, Mexico, and India, that type of thing. So you can think about conduction band being, let's say, India, the valence band being Mexico, and the trap level being, let's say, USA. So then you can clearly see the analogy I'm talking about in that context. Okay. Now, this view that I just told you about is fine, but for mathematical purposes, a slightly different point of view is often useful. So you see what happened in the left-hand side picture. The left and the right are exactly the same picture but treated in a slightly different way. In the left picture, as I told you, is a recombination process. One electron from the conduction band was lost through the trap. Eventually, one holes from the valence band was lost. So at the end of the day, one electron gone, one hole gone. That's the status of that. Look at the right-hand side where I have drawn the process 3. Process 1 is exactly the same, but I have drawn the process 3 in a slightly different way. What I have said here, that instead of the electron coming down from the trap to the hole in the valence band, instead what we'll think that as if a hole has jumped up. Hole has jumped up to the trap and they have met at the trap. The electron and hole, they have met at the trap. Now you see what's the consequence of this. At the end of the day, one electron is gone, right? It came down to the trap. One hole is also gone because it jumped up from the valence band to the trap. And there they recombine. So at the end of the day, the trap is also gone. There's no electron or hole left in the trap also. Exactly the same process, right? In terms of as far as electron number and hole number is concerned, exactly the same process. Now, what about the other process, 2 and 4? So let's think about that. 2 and 4, remember what happened? One electron jumped up from the valence band to the trap, and then eventually from the trap to the electron. How do they get this energy, by the way? They may string up a bunch of phonons and then get help of a photon to eventually go up there. Remember, going up is very difficult. Coming down is very easy. It's like getting good grades. Getting a D is probably easier than getting an A. Now, the equivalent process on the right-hand side is something like this. I have put together, you can see a red and a white on the right-hand side. So I have one electron and one hole, but they are together. At the end of the day, one electron goes up from there. It started from there, both of them, and the hole jumps down. Look at what happened at the end of the day. Isn't it exactly the same as it is from the left-hand side for 2 and 4? Why is it exactly the same? Because at the end of the day, I have one extra electron in the conduction band, one extra hole in the valence band, right? And nothing left behind in that trap level. So these are exactly the same process. So instead of the physical picture, physically what is happening, we'll work on this picture. Because then you can see that things will get in and out of the trap level. And that will be easier to keep the bookkeeping of. Okay? Now let's think about it. The first is we want to look at the number of electrons. So we're focusing on, let's say, India, the conduction band on the top. And we want to see how many people come out and how many people go in. Now, the only state that conduction band communicates with, exchanges electrons and holes with, let's say, is the trap. It doesn't know, as far as compared for the previous picture, starting from the previous picture, it doesn't even know holes, valence band exists, right? Because valence band is only talks to through the trap. So therefore, only thing I need to draw when I'm thinking about how many electrons getting in and out of the conduction band, I just need to think about the trap, and that's it. So how many electrons in the conduction band and how is it changing with time? So I will have to consider process 1 and 2, right? And that's why I have written the subscript 1, 2. So these are the two processes I have to think about. Now think about the first process. First process, so remember in the last class I told you about these electrons are swimming around, this black electrons swimming around, and then there is this trap sitting fixed in the real space. And once in a while they capture, if they are empty, then they can capture an electron and then become filled, right? In the last class we told you about that. And this is exactly that process. Look at that n. N is number of electrons. If you have more electrons, of course it will get captured more. P sub t is number of traps that are empty. Of course it has to be empty, otherwise how is it going to catch any electron? And C sub n, that is the capture coefficient proportional to the velocity. Because if it is running around quite a bit, then the probability of getting captured is more, right? So proportional to the thermal velocity, you saw that in the last class. Why is there a negative sign? The negative sign is because of process 1, the number of electrons is reduced. Because anytime they are captured, as far as electrons are concerned, it has lost a partner. So the number is reduced. What about the process 2? Well, process 2 is, you can see that first I'll explain what E sub n is, but nt is the number of electrons that can jump from the trap to the conduction band. Remember, it was the process 2 just a little bit before. That is proportional to the number of traps that has electron. If it has no electrons, how is it going to give up anything? So it's proportional to n sub t. And 1 minus Fc means that when it wants to jump to a state, that state must be empty. Because Pauli exclusion principle, remember? If it is not empty, then it cannot jump. So it's 1 minus Fc, and En is the rate at which it goes up. It's the emission coefficient. Now we don't know, we haven't given any physical explanation of E sub n. We'll do it in a second. We told you about C sub n in the last class. Why plus sign? Well, electrons are coming back. So I have it, as far as conduction band is concerned, I have more electrons now, plus sign. Okay. Now remember, okay, so and correspondingly, I will not explain this a great deal, but you can convince yourself that between valence band and the trap, you can write the same thing. 3 and 4, I'm focusing on the number of holes this time. Again, Cp, P and N sub T. P is number of holes, N sub T is whenever they are occupied, because holes are captured by occupied traps. Remember, that's when it has large cross section in the last class. And correspondingly, it has the emission probability. So I hope that you will try to understand this one. That's it. I don't need any more equation. I will manipulate this equation a lot, but this is the basic equation, and I'm actually done. So now think about this word. Look at the title, detailed balance in equilibrium. Of course, it's redundant because detailed balance can only happen in equilibrium. Out of equilibrium, it cannot happen, right? What is detailed balance? Every country, every pair of countries, in that case India and Mexico, let's say, everybody has individually the net rate is 0. That's detailed balance. Steady state doesn't have detailed balance, remember. So every state, pairwise, they exactly cancel each other. So since this thing is in equilibrium, I'm assuming, since it's in equilibrium, I will turn out on the light a little bit later. But since it is now in equilibrium, sitting on your desk without any external stimulation, then I can write this dn dt. Because of detailed balance, what should the result be? There should not be any net change in the number, right? Number of electrons should exactly remain the same, independent of time. So I should set the left-hand side to 0. I can only do it in equilibrium, cannot do it any other time. Now, do you notice that I have done something which is a little fishy here? I have taken out 1 minus Fc. Do you see? The second term had the 1 minus Fc. I can only do it, I cannot do it in general. I can only do it if the semiconductor is non-degenerate. That Fermi level is way down. You have few electrons on the conduction band. Remember, Ni is 10 to the power 10. So most of the places are empty anyway. F is very close to 0. So I have dropped it. In general, if I give you a new problem where the level is degenerate, Fermi level is up in the conduction band, don't take this, make this extra step, right? Okay. Now, once I have this, you see here, I know if I somehow could find out this N sub T and P sub T, all those quantities, and I'll show you how to, then a beautiful relationship between these two and detailed balance says that E sub n, the emission coefficient, is actually related to the capture coefficient. You see, it has to be. If the total thing has to be balanced, then the rate at which you capture must have some relationship with rate at which emit. And this detailed balance will allow you to connect the two coefficients. In fact, detailed balance is a way in which in any rate equation, this is semiconductor physics, you can take anything. You can take geophysics, you can take astrophysics, anywhere. This notion of detailed balance is so powerful, it will always connect two processes or a couple of processes in equilibrium, right, to each other and thereby reduce the coefficient by a factor of 2. It's a very powerful technique. So one thing you see that emission is related to the capture coefficient multiplied by a bunch of constants, and we'll think about what those bunch of constants are. I put a 0 there. Why? Because this is in equilibrium. So that's why all these numbers carry a 0 around. Okay. And the whole thing, n0, p sub t0 and the numerator together, I will give it a name called n1. I'll just give it a name. It's no physical significance, nothing. I'll just call it so that I don't have to write too much. And in general, you see, as soon as En and C sub n, emission and capture are related, in the previous equation, instead of having to carry around E sub n, I'll insert n1 multiplied by Cn. You see, I haven't done anything. So long I don't know n1, I haven't, that's just a substitution. Haven't really made any progress yet, but we will. Okay, so 3 and 4 is your homework. You should be able to see the same thing. And again, notice on the top line for the whole rate, I have eliminated F sub V because that was the number of holes in the valence band. I haven't written that because this is non-degenerate. Had it been degenerate, I must carry that around, right? And again, you see exactly the same thing, but this time, whole emission and whole capture, these two coefficients are related to each other. And the valence band only talks to the trap level. So therefore, on the right hand side, I have just kept them 2. I haven't even written up the electron number here, right? Now let's think about it. I just defined N1. I didn't know what it is. It looks like a bunch of constants. And I also will get correspondingly a values of P sub 1. Now look at the magic here. That if I multiply N1 and P1, I don't know what they are. I don't know. But if I multiply, you will notice amazingly that everything cancels. Only thing that remains is N0 and P0. Do you see that how it cancels? The trap occupation, how it cancels? And N0 and P0. Why am I writing it Ni squared? Because remember, this is in equilibrium. This is in equilibrium. So the number of electron concentration and the number of hole concentration, regardless of whether there is trap or not. If there is trap, good. If there is no trap, that's even fine. It's always equal to Ni squared. That's the mass action, right? Remember, that's why I said it's very important. It really doesn't depend on whether it's doped, undoped, whether accepted, donor, trap, doesn't matter. This is always true. And therefore, since N0 and P0 in equilibrium is equal to Ni squared, somehow if I can calculate N1, I'm done because I can calculate P1 by using this relationship. Remember, right? This is where the quantum mechanics hides Ni squared because it is effective density of state, Nc and Nv, and the band gap on the exponential. Do you remember that? So this is where the we are carrying along the quantum mechanics, just it's in a disguise. So you don't see it, but everything is coming with us. Okay, so now I want to calculate N1 because once I calculate N1, I'll be in good shape. So first of all, in order to calculate N1, I want to know how many traps are occupied. Now, if I want to know how many traps are occupied, did I write it correctly? I should have multiplied F naught, right? Okay, let me double check on this one. I think I must have written it correctly, but let me double check on this one. But NT0, let's say I multiplied by F00, which is the number of when it's empty. So this is fine. When it is occupied means when it's not empty. And F00 means when it's nothing is there, right? No electron is there. So this is fine. 1 minus F0 means when it is occupied. And when it's occupied, that's N sub T. So I multiply. Remember the derivation from before for the donor level? Remember, there's no difference between a donor and a trap. A trap is a donor in the mid gap. Why is it? Why they have different name? I'll tell you a little bit later in the next class. But I should be able to use the same formula for donor. Had it been below the conduction band, I should be able to use the same formula for the acceptors. So it's the same formula. So I put that in. G sub D, do you remember what is that? Degeneracy factor, right? For conduction band, for silicon it is 2. And for valence band, for silicon, 4, right? So we remember that quantity. Here we know beta is 1 over kT and E sub T is the trap level. We know that. Copper, where is it? Or gold, where that level is in silicon. We know that, so we can put it in. Now let's try to calculate this thing. Now, do you agree with this statement that P multiplied P sub T is when the trap is empty? When the trap is empty means it doesn't have any electron. That means N sub T is a total number. The fraction which has lost both its electron is multiplied by F sub 00, which is the blue F sub 00. So that's the numerator. And in the denominator, I also have the expression for N sub T. Okay, and these are all in equilibrium, remember. That's why I'm carrying around the 0 in the subscript. Okay, now you already know the expression for F00, so let me not worry about it. You just insert the whole thing in, and once you do, you see you get an expression for N sub 1. What is that? Do you see whether you know everything on this one? Ni, do you know that? You know that, 10 to the power 10, right? That you know. G sub D, you know, degeneracy factor. What about ET? Well, you look at the table, whatever the ET is. Do you know EI? E sub I, the intrinsic level, do you know that? You know that, because remember we said in equilibrium, N is equal to P, and from that we calculated the value for EF, and EF is EI for the intrinsic material. Do you remember that? It's close to the mid gap. I have EI. This whole thing I know. And therefore, I know N1. Where is silicon hiding in here? Silicon hiding is in Ni, because if you change it to germanium, Ni will be different. G sub D, this is where E, these are the various places the material constants are hiding. If I know N1, do I know P1? Well, of course, because of this. And because of that, I know P1 as well. I'm done. You see, this is math. There's no deep physics in here. Just have to keep track of a few lines of algebra. Okay, I'm done with this one. N1 I know, P1 I know. I can go forward now. Now this time, I'll look at USA, which is sort of the trap level. Previously, I looked at the conduction band and the valence band. This time, I'm looking at the ELO region, that how the electrons are coming in the trap and getting out of the trap. Same for the holes, right? So how would you do that? So let's look at this. So I'm looking at how the trap concentration is changing. Trap occupation is changing as a function of time. First of all, see whether you agree with this. I have written as a minus of the change in the electron concentration. Does it sound right? It is right, because anytime a electron is lost from the conduction band, that loss is the trap level's gain, because trap got 1. When the electron, conduction band is unhappy, but trap is happy, it got an extra 1. They have a negative sign. What about holes? The holes the same way, because I'm looking at occupied number of traps. Anytime the hole concentration went up, right? How did it go up? because electron jumped up to the conduction band. That's why its whole concentration went up. Because it jumped up, as a result, I will have a plus sign for this one. Please try to convince yourself that this is a correct statement, right? If I give you 2 trap level in exam, not that complicated perhaps, but you should be able to do this detailed balance, write the equation at least of the trap level, right? Instead of having 1 level. Now, I already know the expressions for d and dt. I just derived it in the last few slides. I know that. And I also know that for the dp dt. I'll just flip the sign and put it in here, right? And the En and Cn, Ep and Cp, well, they are all related. So I'll put them all in here. So I'm getting an expression. Here I essentially know everything. Do you see that? Look at this equation. Cn, I will calculate it multiplying by sigma, the capture cross section from the last class, and the thermal velocity. Do you remember last class? Cn I know. If I know Cn, I also know C sub p. Now N and N1 I know, I just calculated, and N sub t is what I'm trying to calculate. And P sub t is 1 minus N sub t, or Nt minus N. So except from Nt, I know everything on this equation. I should be able to solve this. So now I'm talking about, that's the general case. If I solve that one, I should be able to solve in every case. Transient, steady state, I should be able to do any problem. That is the general equation. Always true. Single trap level, non-degenerate. Always true, that equation. But if I insist that it's in steady state, then what's going to happen? In steady state, what will happen, that although the trap level talks to the conduction band and to the valence band, right? It talks to many different people. Individually, they will not be balanced anymore. Why? Because this is no longer in equilibrium, right? They are no longer in equilibrium, so they will not be individually balanced. However, globally they will be balanced, that there will be no net change in the population in the trap as a function of time. So I set that thing to 0. So now I can solve for N sub t. This I can easily solve for this. You can just work out the algebra. This is one line of algebra. I'll not go through that. And let me just look at the net rate of recombination. So remember, this is in steady state. That means all rates are the same. The rate at which electrons are disappearing, the same rate at which the holes are disappearing, right? Net. It has to be the same. So if I just wanted to calculate the flux that is at which it is disappearing, I will just say the recombination is minus dp dt. And from the previous expression, if I substitute the value from the previous slide, substitute the value of N sub t, I have the whole thing. Very complex looking equation. This is what terrorizes solid state students. But it's not that bad. I'll show you. Do I know everything here in order to calculate the trap number? If somebody gave me N and P, if somebody did, then everything else is known. N sub t, the number of traps, right? I know the number of traps. I know all the capture coefficients. Ni squared I know. So I should be able to calculate this. And that is, I'm going to give you some example. But before I proceed, let me quickly ask you something. You see, in this one it says in equilibrium, if I wanted to look at equilibrium, in equilibrium, the rate must be 0, right? And then the only way this whole thing can be 0 is if Np is equal to Ni squared. So this is an important statement. When we derived the law of mass action, we just multiplied two things and it came, Ni squared came out. And it didn't really say how violently electrons are moving around. But you can see actually Np equals Ni squared actually comes from a detailed balance condition like this. Here the electrons are coming down from the trap, they are going up through the trap, they are all around, and at the end in equilibrium, Np is Ni squared. See? So that is somehow is getting reflected in this expression. So equilibrium is not a retired person's life. Equilibrium is a very active person's life, but all the processes are balanced. It looks stationary. And this, instead of carrying it around, we'll call this whole quantity tau sub n. This is minority carrier recombination time for electrons, and tau sub p, this whole thing in the bracket, just to make it look nice. And that is the whole recombination time. Okay, let me show you a few examples. Derivation done. So let me show you a few examples how to use it. Let us consider a semiconductor in which you have shine light on it, right, shown line on it, but not very strong light, just a few extra electron hole pairs. So let's say on the order of maybe 10 to the power 12, 10 to the power 13 in silicon. Ni is 10 to the power 10, right, per centimeter cube. Very weak light, I've shown. That's why the word low level injection. So the number is not very high. How will I know how the electron and hole, after I turn it off, how will it disappear? Let's look at this. The way it will disappear is by something like this. So I have this electron and holes. Now I have written n as n naught plus delta n. Now delta n here does not mean it is small in general. Don't always assume that if I have a delta, it always means small. In our context, it will not be. So in general, I can always write it n naught equals, n equals n naught plus delta n, and p equals p naught plus delta n. Why do I write delta n, not just delta p? Because I shine light in it. And the number of electrons that was generated must have left behind a same number of holes. And so the number of electrons and number of holes in this special case is exactly the same. So therefore, I write delta n and delta p equal to each other. That's what I have written. Now it can be simplified a little bit more. And let's say whether you agree. The first term on the numerator, n naught multiplied by p naught, what is that? Ni squared. And you can see that will take care of the last term on the numerator, Ni squared is gone. And you can see if you cross multiply this, then you will have a delta n multiplied by a constant and delta n squared. And you have the same bunch of things on the denominator. Now if it is small, low level injection, if delta n is small, delta n squared is even smaller, right? So I'll get rid of that. Similarly, if this is a p-type material, p-type means it has a lot of acceptors, then it has a few electrons, right? Relatively few electrons. And so which term can I get rid of? I can get rid of n naught. Why? Because it's a p-type material, lots of holes, few electrons. And that's why I get rid of the n naught compared to p naught. You see, you'll have to make relative comparison. And once I have done that, I will simplify in every case. For example, I can get rid of n naught from here, and delta n is small compared to p naught, right? And so I will get rid of that, the whole term, and only thing that remains is p naught, because p naught is much larger than delta p because of it's a low level injection. So I'll get rid of this. Now this step you'll have to follow step by step. When you go home, follow step by step. But at the end of the day, look at that expression, delta n divided by tau sub n. So how will it decay as a function of time? This is dn dt, right? That's the rate of change. It's proportional to delta n over tau n. So it will go down exponentially as a function of time, right? That is how it will going to decay. So the few electrons you have pumped up in the conduction band, they see a sea of holes all around it because it's a p-type. And they bump in the holes all the time through the traps and keeps recombining. So therefore, you don't see the expression for anything related to the holes here. You see, there is delta n over tau n. Because holes are so numerous, anytime it wants a hole, it will get a hole. So as a result, I do not have anything in the final expression related to the holes. You see, that's not a rate limiting supply. You have to understand the meaning of the equation so that you remember it exactly. High level injection, same procedure, but now you have shone a very strong light. Let's say you have put a laser on a bunch of, a little piece of semiconductor. Semiconductor was intrinsic to begin with. Huge number of electron hole pairs. So therefore, what are you going to do? So you will expand it the same way, but this time, unfortunately, you cannot leave out delta n squared. In fact, delta n squared is much larger than the first term around, right? Because ni, let's say, is 10 to the power 10 or so. Delta n, if it is 10 to the power 18, then this whole second term will be significantly larger. The tiny amount of electrons and holes you had in the beginning doesn't matter because the light has generated so many. And so you will put it in. And this time you'll see that instead of just tau sub n, you have tau sub n plus tau sub p. Why is this? Does it physically is like this? Because now the electron and hole number are almost equal to each other, right? Nobody is dominant. So therefore, it will depend on how quickly they can find each other. It is not that anytime electron wants, there is always a hole, or the vice versa. It is here, both are limiting. You have to find both at the same time in order for the recombination to occur. So therefore, you have tau sub n plus tau sub p. High level injection, right? Okay, and the previous one was low level injection. By the way, this very quickly, so in organic solar cells, a topic I am working on recently, these type of processes are very important. Organic solar cells are essentially intrinsic, right? But the sunlight comes in and it generates a huge number of electron hole pairs. When they recombine, this is the process with which they will recombine, not the low level injection process. Now, let me ask you this. Is which one is higher? In one case, I have a delta n in the numerator, and another case, I have the a little bit bigger numerator, a denominator compared to the other one. But you see, high case has a bigger denominator. Does it mean at a higher level of injection, you have lower recombination? That makes no sense. So what's wrong? Exactly right. So the delta n for high level injection, although they are both delta n, one delta n is 10 to the power 18, another delta n may be 10 to the power 12. So although it looks like that the first case is actually looks like smaller, actually first case is orders of magnitude higher because they will recombine very quickly, right? It has lots of electrons and holes. So that's why the expression looks funny, but it is correct. Now, what happens if somehow, and this will come later on when we talk about diode, somehow you can take out all the free electron holes, take them all out. Now, if you take them all out, then n is 0, p is 0, because I took them all out. So, if I take them all out, then I have ni squared on the top, and you can see that I have taken out n and p from the denominator, and it's a constant, I know. The important point I want to show you here is in the previous cases, I always had a plus sign. R was delta n divided by tau n. In this case, I have a minus sign. What does it mean? It means the previous case, there is lots of electron hole pair, they were recombining and they were going away. The number was going away. This time, this is being generated because there is no electron and hole. It wants to go back to the 10 to the power 10, right? So it will keep generating until it can reach the equilibrium. And therefore, I have a minus sign here. It is inverse of recombination, generation. So that is what I have here. Okay. Now this again, I'll show you in devices. Everything I'm doing, every step will be used in the subsequent lectures. So it's important to know how it works. Now, the two remaining processes I'll talk about is direct and OJ recombination. Direct recombination, I'll not even try to, I'll just make an analogy and let it go with that. You see, in the recombination, generally what we had in the denominator, we had, numerator, we all had NP minus NI squared. That says in equilibrium, that thing must vanish. In the denominator for the Shockley-Reed Hall, we had things proportional to the trap concentration, right? NT, capture cross section, and all those. When you have direct recombination, an electron coming in, recombining with holes, I don't have any traps or anything. So the whole thing that I had in the denominator, I'll just replace it with something called a B. Now, of course, I can derive it properly. This depends on the band gap and other things, but that's another class, maybe 659. They will derive it properly. But for now, let's assume that it's a simple formula, or life is simple. And if you want to handle low-level injection in gallium arsenide, direct band gap material, then you will just do this. It's a p-doped material, let's say. You'll expand it, and you will drop terms. You will say delta N is equal to delta P. The second order squared term you will drop, and eventually you will get an expression for proportional to delta N, the excess generation you have. What is tau direct? By the way, tau direct is the rate. So this first term, B multiplied by P naught, that is the rate or time constant with which the extra electrons and holes will disappear. This time you see it has the number of holes, because if you have more number of holes, of course, that allows you to recombine faster. Okay. Similarly, you can say what happens if I completely remove electrons and holes from a given region. Okay, this is no problem. N and P is 0. So there is a net generation upwards and given by B Ni squared. Why do you find B? Well, this is listed in the tables. In every material, somebody, if you just look up a handbook, they will tell you what the value of B is for a given material. OJ recombination, again by analogy, look whether you can understand. Does it look right? Let's start with the red one, the red first term. I write it as N squared P. First focus on that. N squared P. Does it look right? Because two electrons have to bump in against each other. N squared. And P, well, it has to find a hole in order to get in, right? So therefore, it's multiplied by P. Now, in principle, I should have written a 1 minus Fc for the second electron to go up. But at that level, everything is empty. So therefore, only thing I have is N squared P, right? Now, why do I write Ni squared N on the right-hand side, on the second term? The reason is this term must vanish in equilibrium. Does it vanish in equilibrium? Do you see? Because in equilibrium, N will be replaced by N naught. N naught by multiplied by P naught, what is that? Ni squared. And you can see that this term will vanish in equilibrium. So this is necessarily, it's not a derivation, but it looks right. Do you see on the other hand, on the second term, we're multiplying C sub P, that there is a P squared multiplied by N. This says two holes bouncing each other. So with so much energy, one electron going in the conduction band and another going deep down in the valence band. That's the second term, and that's where it comes from. These constants are measured. People, and in fact, I spent many years, or not, at least few years in my life working on semiconductor lasers, and I really had to go through the intricacies of the physics here. But for you, one slide is more than enough, hopefully. Low-level injection, you should work it out. Again, put these conditions in, and once you put this condition in, you will see that if it is a p-doped material, you will see that P squared will become Na squared, because P is equal to Na. The number of holes equals to the acceptors. So you can put it in, and you will see that the recombination in this case, the OJ recombination, if the doping is very high, Na is very high, in that case, OJ recombination will be the dominant recombination mechanism in many semiconductors, right? Because you see, Na squared. Why did the Na squared come from? Because that's the P squared over there. You need two holes. And when you have high values, because it doesn't have to conserve momentum directly, remember that was the problem, same wavelength, that was the problem. So when you have lots of electrons, you can bypass that conservation problem and therefore have very rapid recombination through the OJ process. So let me I think let me show you just one slide and then I will end, because I think I'll pick it up in the next class. So now consider we have all this complicated derivation. So let's take a step back. The semiconductor doesn't know that you are grouping things into Shockley-Ridgeway, direct, OJ. When an electron goes up, yeah, when you shine light, it will go down in any path it can find. Direct, available, good. If it doesn't have a direct path, it will take the Shockley-Ridgeway path. It will take any way it can go, it will go down. So when you shine light and let the light be off, turn it off, then it's going to go down from experiment, I'm saying. And in experiment, if you look at the output light that is coming out, you will see it is decaying as a function of time. So x-axis is time, y-axis is delta n. And I am t equals 0 in this one is when I have turned the light off. Just turn the light off and I'm looking how the photons are coming out. So from experiment, what I will get is something called a tau effective. That's how I'll see the whole thing decaying. Now from that, how am I going to get this various coefficients, C7, the capital B for direct recombination? How am I going to do that? So in order to do that, you'll have to understand how these recombinations actually depend on various things. So as I said, all processes will work simultaneously. And this all recombination rates will be together. But I just told you that for each one of them, remember this is low level injection. So every one of them is proportional to delta n. I have a Shockley-Ridgeway time constant, I have a direct time constant, and I have a OJ time constant. This I just derived in the previous 3 slides. And this, each one of them has a certain dependency. The first term, the Shockley-Ridgeway, it depends on the number of traps. The direct, it doesn't care about number of traps because no trap is involved. Only thing it cares about is the number of dopant atoms, right? Why? Because it gives you a certain number of holes or certain number of electrons. OJ, yes, it depends on the number of dopant atoms, but as a square, because 2 of them have to bump against each other. So they have different dependency. So if I do a set of experiments in which I'm changing the dopant level systematically, then this decay will be different for each one of them. And from that, I should be able to pick out what these different coefficients are. You see? So this is what it is. This is from your book, and I want to explain how did they get this one. So y-axis is tau effective. So from experiment, somebody shined light on it, on silicon dioxide, and they saw how the whole thing is decaying. And they just put one data point on each one of them. X-axis is number of dopants. So that's the x-axis. So on the left-hand side is close to intrinsic. On the right-hand side, heavy doping effect. Remember? Heavy doping effect we talked about. So that's happening on the right-hand side. Let's see whether we can understand this. The tau effective should be the sum of all these things. Now in the left-hand side, n sub d is close to 0, right? It's close to intrinsic. So that means the second and the third term will drop out. At the low side, it will drop out. So from there, if I know the number of traps, I should be able to calculate C sub n. Right? So that's good. Now if you go at a very high doping side, then you see the first and second term will drop out. Why? Because these are actually smaller terms. The third term will now be humongous because it's nd squared. Now remember, this is a log-log plot. So if you take a log-log on the tau effective on the left and right hand side, what should be the slope of that line? -2, right? Log, if you take a log, and if you look at this curve, you will see exactly -2 is exactly the value on this curve. The slope and the high side is exactly the value on this curve. And experimentally, people have seen exactly very similar. That's theory. That's the theory. So you put various values of ND you can generate the curve. But experimentally, I have shown you from 2 different papers that indeed at high density, this is 10 to the power 20, very high density, right? 1 atom in every 100 host atoms, very high density, and you can see how the things are falling off. So from here, if I give you a curve like this, from here, by looking at the slope and looking at the intercept, you should be able to calculate back the OJ recombination constant. Is that right? And from our lower values, you should be able to calculate the number of traps, because actually from that you should be able to deduce all this. Okay. All right. So this is all about recombination, that how equilibrium is restored. We perturbed it with light, and we said that the Shockley et al. Recombination, this is one of the things you have to learn, unfortunately, in order to earn a 6-figure income later on. But hopefully this was not too painful. And this is an important recombination mechanism. That's the dominant thing. That's how you design your, anytime you carry a stick, memory stick. Many are DRAM memory you buy for your computer. All of them actually, the people who design them understand how this recombination mechanisms work, because you are allowed to lose only 1 electron in every 10 years. Because some of the memory that has so few electrons in it that you cannot lose any electron. Because if you lose 1 in a year or 1 in a few years, that's also even too many. So this recombination mechanism, somehow or other, you have to have extreme control over before you can have a viable product that you can sell. It looks a little complicated, but if you follow through the steps, and why don't you do this exercise where instead of having 1 trap level, you have a pair of trap levels, and see whether you can derive the detailed balance for this. You know, it's no rocket science here, very simple thing. Now, direct band-to-band and OJ recombination, I use the very similar formula. They have their independent derivation, but generally for direct band gap material, Shockley et al. Is not that important. This direct band gap and OJ recombinations are the dominant thing. Especially for laser, OJ is the dominant process. And this is not just some theory. For last 50 years, hundreds and hundreds, maybe thousands of engineers and physicists have done beautiful measurements. You know, those looks like few data points, but who did it really had to work hard to set up the experiment, shine laser on it, get the electron hole pair out, and see how they are decaying as a function of time. A beautiful experiment that has been done. Hopefully some other course we'll have an opportunity to discuss them. Okay. All right then. Thank you.